The regeneration of lost tissue relies on the use of biomaterials, which act like a scaffold for new tissue to be formed. When a biomaterial gets inserted into a tissue, it gets in contact with blood and absorbs plasma proteins. Now, some of these proteins, the smiley faces here, are clinically useful because they trigger the host reactions, such as blood clotting or cell attachment. Now, what would happen if we could specifically increase the affinity of a material to a desired protein? A protein that can promote cell attachment to the biomaterial, for instance, by expressing a molecule, a receptor that binds that protein and that protein alone. When this biomaterial is now inserted into a tissue, it still absorbs proteins, but due to its enhanced affinity toward a desired protein species, it would be mostly enriched for that protein species. But how to provide specific receptors for desired proteins? To this purpose, we used aptamers. Aptamers are small pieces of DNA which can be engineered to specifically bind the target molecule, so they behave like antibodies, but they're smaller, they're invisible to the immune system, they're non-animal derived, and can be synthesized in the lab. We have teamed up with an American biotech company, Base Pair Biotechnology, to select aptamers for molecules of interest to bone and cartilage regeneration. Now, when we take a scaffold from the comers and plate cells, nothing gets attached. The biomaterial is empty, but when we use our aptamers for adhesive proteins, cells like it a lot. Any biomaterial can be enriched with aptamers, and you can see some example here of what the final product could look like: an injectable bone biomaterial or a bone substitute. Because aptamers are science. But using aptamers to create bioactive scaffolds and improve the life of patients is art.